just kicked me out.
No, it was the oddest thing, and it worked out because we got out 10 minutes early. Okay guys, just a heads up and a reminder of what's going on. Okay, we're going to finish up graph theory today, hopefully, right, depending if I fall over or not. Make sure that for Monday, if you have any questions when you're at the final exam, you can bring those to me. I'd be happy to answer whatever I can. I'll just outline what's going to be on the final like I usually do for the exams, and you guys can ask me questions that I choose. Okay. All right. And then on Wednesday next week, if we finish up everything for the final, I'll be available for individual assistance. I'll just either sit in the room or sit in my office and just assist. But if you guys feel like you're comfortable with the final, then we don't have to show up to class on that Wednesday if you don't want to. Okay? For the assignment, just take a picture of it and send it to me by 3:15 p.m. so I can do something. All right. So if you don't want to come to campus and you don't have class, all right, you can email this to me. Or you can just drop it off to me, whatever you guys want to do, make a paperwork. What's that, sir? Oh yeah, you can give it to me Monday if you guys are done with it. I don't care. But I'll make it due Wednesday so that way if you guys need an extra day or two, then that's fine. Okay. And then our final exam is going to be the Wednesday the 14th. It's the 2-hour examination block, so I just made it scheduled for that time. Okay. So everybody clear as to what's going on, guys? Any questions before we get started with more graph theory stuff? Okay, so we're getting there. We're close. Okay. I think last time we talked about complete graphs and bipartite graphs. So the next, I guess, logical thing to talk about is the difference between a path and a circuit and a walk and those sorts of things. Okay, so we have our definitions. Basically, a walk is anything goes. Okay, so if I talk about a walk from one point or from one vertex to another vertex, it's any sequence that you want to end up and begin on the same vertex. Okay, so walk is the most, I guess, free or liberal or forgiving type of traversal of a graph. Closed walk basically means you begin and end on the same vertex. You could bounce back and forth between the same vertex a million times if you wanted to. It's still a closed walk.
So a walk is like from all the vertex?
Yeah. No, it doesn't have to be all of it. Like for example, if I wanted to do a walk from 1 to 5, I could do 1, 3, 5. I could do 1, 2, 5. I could do 1, 2, 5, 2, 5, 2, 1, 5, 1, 5, 2, 1, 5. A walk is anything I want it to be. Doesn't matter. It doesn't have to be the original route. Okay. Walk is just definitive a traversal. Closed walk means you start and begin on the same. A path means you can't repeat edges. Okay, so that's where it starts to get a little bit tougher to work with the traversals. So you can't repeat any edges. Simple path is basically going to be a path with no repeated vertices. Okay, so path is no repeated edges. Simple path, no repeated vertices. Some of you guys, I think, last time might have confused a circuit with a loop. Okay, a circuit is basically going to begin and end on the same vertex. So in other words, it's a closed walk, but you can't repeat edges. Okay, so it's different than a loop. A loop is basically one edge, you begin and end on the same, but you only do one traversal. Okay, circuit you can just do as many as you want. Simple circuit is the most difficult. Circuit that does not have any repeated vertices except for the first and last. Okay, so basically I went from the most free, if you would, or the most forgiving down to the least forgiving. Okay. So what I wanted you guys to do is just go ahead, we can define a few of these. So I want to try to find a path from 1 to 4. Okay, we go up to the definition of path. Path basically means no repeated edges. Okay. You can just name the vertices if you want to, since each vertex is only, I guess, joined by adjacent to one edge. Right? So if I want to go to 1 to 4, all right, what's one possible path that I can use?
V4, V5, and V1?
Well, it would start at 1.
Oh, yeah, it has to start at 1.
It starts at 1, so we'll go from 1 to 4.
Oh, so V1 to 4, right? So
Yeah, we could do
V1
V1, 2, V2, 5, V3, 4. That's certainly one possible path.
That's a walk you're talking about?
No, this is a path.
Oh, okay. So
Okay.
a path in general, a path that contains the vertices and the edges.
Well, it just, you can't go back over vertices. Or I'm sorry, you can't go back a path, you can't go over edges. You can't repeat edges. So once you've gone over that edge, you can't repeat it. Okay?
So why do we care about the vertices then?
Well, we have to denote which of them we're going through in case for some reason you have some sort of vertex or you have an edge that might go to somewhere else that it just makes it more definitive.
Right.
Okay. So for instance, we could say for letter A, we could say 1, comma, v sub 1, comma 2, comma v sub 2, comma 5, comma v sub 3, comma 4. Okay? So, or you could just do the vertices, I really don't care. Okay? The only downside to that is if you start having parallel edges, then it might matter in that instance. But because none of the edges are parallel in this graph, we don't have to worry about that. Okay? Does that make sense, guys? It's as easy as it gets. Okay. Find 3 walks from 1 to 2. All right, this one you can't really get wrong. Okay, well you could, but that'd be embarrassing. What's the easiest one?
V1.
Yeah, 1 V1 to 2. Right. So 1 comma V1 comma 2. So that's one of them. Okay. Another walk from V or 1 to 2 would be what, guys?
V6, 5, V2, 2.
Yeah. So 1 V6 5 V2. So 1 V6 5 V2 comma 2. Okay. If I really wanted to, I could repeat some of the edges. So I could go 1 comma V5 comma 1, or sorry, comma 3, comma V5 comma 1 comma V1 comma 2. All right. So, and like we say, guys, a walk can be anything it wants to be. All right.
What you write? 1 comma V5.
V5 comma 3. So 1 to V5 to 3 to this should be V5. That's a 5 in English. So, and then 1 V1 2. Okay, does that make sense?
Yeah.
Oh.
V2, 5.
So you like went over the back then?
Yeah, with a, and remember with a walk is anything it wants to be. Okay, so look at your definitions, guys. Definitions are going to tell you what you have to do, what you're allowed to do, and what you're not allowed to do. Okay. And then finally, if I want 2 circuits from 1 to 1, obviously.
I think you got it, the last one. Hold on a second. 1 comma V5.
Yes.
Then
comma
3,
comma V5.
3 comma
V5.
What is V5 again? Hold on a second.
Yeah, same thing.
Oh, okay, you're coming back. Okay,
Comma
okay.
V5, comma 3, comma V5, comma 1, comma V1, comma
Okay, gotcha.
Okay?
Uh-huh.
Okay. All right. For C, find 2 circuits from 1 to 1. So I think the easiest one would just be 1 V6 5 V2 2 V1. Remember, a circuit basically says you have to begin and end, and you can't repeat any of the edges. Okay. So that would be 1 comma V6 comma 5 comma V2 comma 2 comma V1 comma 1. Okay, so that's one possible circuit. Another one you could do, you could just go on the outside or the perimeter. So 1
Uh-huh.
to V6
Okay.
to 5 to V2 to 2
Oh, and
to
then come.
V1 to 1.
Okay,
That's a
okay.
circuit. You just go and you begin and end on the same. Okay,
Right.
does that make sense?
Mhm.
Okay. So that's one possible circuit. And then for the other one, you could just trace the perimeter if you would for this. So we could do 1 comma V5 comma 3 comma V4 comma 4 comma V3 comma 5 comma V2 comma 2 comma V1 comma V. Okay, so any questions I can answer, guys, about how you guys are going to do the traversals and the 6 different possible traversals for a graph? Okay, really easy stuff. Look at the definitions. The definitions are going to tell you what you're allowed to do and what you're not allowed to do. Okay. All right, specific types of circuits. Okay.
Let us see.
Okay. So an Euler circuit is essentially going to be any graph G. Okay. It contains every vertex and every edge. Okay. And remember, with a circuit or any circuit, you can't repeat edges. Okay. You can repeat vertices, but you can't repeat edges. Okay. So let's make sure. I'm sorry. You may repeat vertices. Okay. But not edges. So if I look at these 2 graphs, by the way, these are 2 separate graphs because obviously if they were 2 unconnected graphs, then you couldn't find a circuit, okay? There's a number of different Euler circuits that exist for this guy right here, okay? Does someone think they might want to take a guess and tell me what an Euler circuit is? Jake?
F4C, 5D, 6A, 2C3E, 1A, 7, and then just down the right side.
Okay, so B8D,
9F.
B8D, 9. Okay, so let me let you guys copy it down first, and then I'm just going to trace it through just to make sure you guys that is correct. Okay. But I want you to notice that what he did was he only used each of the edges one time. Okay, so I mean I could just look at that and count 1, 2, 3, 4, 5, 6, 7, 8, 9. So at least if it's wrong, I can't really see it right away that it's wrong. Let me trace it just to illustrate that he is indeed correct with this. Okay? So we start with F, and what I like to do is I just like to take a cross, or I like to just draw like an arrow on each of the edges. Because remember, the vertices don't matter. You could step on a vertex 7 times if necessary. So we're going to go to 4, and then we're going to go to 5, and then we're going to go to 6, and then we're going to go to 2, and then we're going to go to 3, and we're going to go to 1, and then we're going to go to 7, 8, and 9, okay? And that begins and ends on F, okay? So if you wanted to, you could just trace it, okay? In fact, there's a multiple, in fact, with what I drew there, if you wanted to start and go 4, 3, 1, 2, 5, 6, 7, 8, 9, that would work too.
Do they have to start and end at the same vertex?
Yes, that's the definition of a circuit.
Circuit, okay.
Remember guys, circuit means you have to begin and end at the same vertex.
Can you start on whatever vertex?
Oh yeah, it doesn't matter. With an Euler circuit, it doesn't matter which vertex you start on, okay? Alright, guys, any questions about this? Yeah, John?
You can like go backwards, like wait for B, like B on the last video.
Well, that's not a circuit,
Oh yeah.
okay? I think B was a walk. And remember, walk is the most, I guess, forgiving of all the traversals, okay?
Okay.
Walk, you can go back and forth 9,200 times if you wanted to, okay?
Yeah.
So like I said, guys, look at your definitions. Make sure that when I ask you for something, it matches up to the criteria shown. Okay? All right, any questions, guys? Okay. For the second one, okay, if I want to try to go through and find an Euler circuit for that, I don't know if anyone was able to do that. So can somebody tell me if they found one?
4D, 2G1F, 2A, 3B, no.
Okay.
Wait,
Start over?
yeah,
Okay, that's all right. It's always easier just to start over if you have.
Is this one even possible? Like, just
Might be.
get that out? Okay.
Oh, that's fine.
Just wanna make sure since lines that one.
Yeah. All right. Yeah,
Okay, never mind.
unfortunately, this is, no, it's okay that you couldn't find one because it's not possible.
okay,
Okay?
It's the D, it's the D that threw it.
yeah.
Right. Guys, I want you to notice, take a look at all the vertices in the first graph. Okay? What do you notice about the degree of all the vertices in the first graph?
1,
They're
2,
all
3,
even,
4,
right?
5, 6, yeah.
So this has degree 2, this has degree 4, this has degree 2, this has degree 4, this has degree 2, this has degree 4, okay? I want you to notice that the total degree of everything is going to be even for this, okay? Guys, if it's even, doesn't that mean you can go onto that vertex and leave that vertex and never have to come back to that vertex if it's even? If it's odd, doesn't it mean that it's possible that you guys might get stuck on that vertex and not be able to leave the island if you would, okay? So, and remember, you can only traverse each edge one time, okay? So, this does not have an Euler circuit. It has circuits, but it does not have an Euler circuit. Alright, and just as an example as to why, we could say that vertex 4, this has degree 3, so we could say degree of 4 is equal to 3, which is odd. So my suggestion would be, guys, go through, look at the degree of a graph. In fact, doesn't it look like degree is one of the most important characteristics of a graph? So if you guys ever have to work with graph theory or you have to work with networking and stuff like that, the first thing you might want to do is determine the degree of that.
2 also has 3 degrees, right?
Well,
Number 2 also.
oh yeah, it doesn't matter which one. It's just I identified 4 because that's the one I was looking
2 has 5, sorry, 5 degrees.
Oh yeah, I mean, it doesn't matter which one you look at. All you have to do is identify one as a
One.
counterexample. Okay? All right, other questions, guys? Okay. So those are Euler circuits. Okay. Hamiltonian circuit for a graph is a simple circuit. Okay. And let's remember what simple circuit means. Right. No repeated vertices.
Except for the first one.
Right, okay, which has to be true, right? You have to be, on a circuit, you have to start and end on the same, okay? So no repeated vertices, except first and last. Okay, I mean, you gotta have the first one and last one repeat. And it also must include every vertex, okay? So we can't skip vertices when we're looking for a Hamiltonian circuit. Okay. It is a sequence of adjacent vertices with distinct edges, which vertex appears exactly once, except for the initial and the final. Okay. All right. Now, I'm not going to explain to you guys or ask you guys to show that it doesn't have a Hamiltonian circuit. It's actually very difficult to prove that a graph doesn't have a Hamiltonian circuit, because we have to know a little bit about bridges and we have to know a little bit about map coloring, which we don't have time for, unfortunately, in a general survey for this. Okay, so let's determine if there's a Hamiltonian circuit for each graph. I want you to notice that I didn't say anything about having to use all of the edges, right? So some of you guys might be looking at this and say, there's no way to do this because I have to use all the edges. That's in an Euler circuit. In a Hamiltonian circuit, you don't have to use all the edges.
But can you repeat
No.
trading on the edge?
No, definition of simple circuit. Take a look back at the
Okay.
definition of simple circuit. Definition of simple circuit says no repetition,
Okay,
okay? So like I said, guys, go back to the definitions, okay? Look at your basic definitions to ensure that the criteria that's outlined matches the criteria for what I'm asking, okay? So, you do not have to use all of the edges, which actually makes it pretty easy, right? Because that way, especially for the first one, I mean, that's really easy. So let's just say for some reason I started on A. I think everybody could find a Hamiltonian circuit from A. So somebody just list out a Hamiltonian circuit if I started on A, please. Just go ahead and trace it. Go ahead, Mark.
A, D, F, H, G, E, A.
So A, B,
No, A, D,
A,
F,
D, I'm sorry. Sorry. So A, D, F, go ahead, man.
H, G, E, A.
H, G, C, E, D.
No, I thought you,
You gotta get them
no,
all.
but you don't have to use, oh, do you have to use all the vertex?
You have to use every
Oh,
vertex.
okay, never mind.
G, C,
Yep.
E, D.
So it includes every vertex in G.
Oh, okay.
G is just.
So let's try again. That's the good news about these, they're easy to fix.
Erasers working.
Yeah, that's true. On like a spider leg airplane. Alright,
Yeah.
so,
A, B, D, C, F, H, G, E,
and what I usually do is I go through, after I find the path, or I'm sorry, the circuit that works, I just go through and trace it, okay, just to make it easier myself. Okay. So A to D, and then B to D, and then C, and then F, and then H, and then G, and then E, and then A.
When we're solving these, is it usually obvious which vertex we have to start at?
No, you can start at whichever one you want, okay?
But it wouldn't be possible with all the vertexes.
Oh, absolutely, it would be.
Oh.
Yeah, you can start at whatever vertex. If there's a Hamiltonian circuit, you can start at whatever vertex you want and find a Hamiltonian circuit.
As long as it's follow the same pattern.
Correct, okay? So,
Oh, I see how that works.
Okay. Yeah. By the way, if you wanted to prove that, if you ever take a course in graph theory, you would actually prove that it has, you can start on any vertex, you can do that by mathematical induction. You prove it works for the K case and then true for the K plus 1. In fact, mathematical induction and graph theory are very, very heavily correlated to one another. Okay? If anyone's interested, I have a pretty good book on graph theory that shows, like, no, you're not interested, Well, guess what, I'm not interested in the future. Alright, that's okay. Alright, guys, any questions I can answer about that one? Okay, the second one's just as easy, okay? Let's just start at 5 this time, just to say we started somewhere different, okay? I bet you there's some of you guys that started at 1, I don't care where you started, okay? Does somebody think they might have a Hamiltonian circuit if they start at 5? So Brian, please.
5, 7, 8, 6, 2, 4, 1, 3, 5.
2, 4, 1, 3. Looks good to me. Okay. Yeah. Sorry. When you have 101 degree fever, sometimes things go wrong. Okay. So we said 5, 7, 8, 6, 2, 4, 1, 3, 5. Okay. Is that what you said, Ryan? I just want to make sure. Okay. What's that rule in psychology? You can memorize plus or minus 2 with 7, I guess. Oh well, that's right. We're math people. We don't care about psychology. Okay. We just like making people feel inferior because we're smarter. Okay. Any questions about either Euler circuits or Hamiltonian circuits? Okay. Really easy, right, guys? You wish your whole final was just this stuff, no induction and all that good stuff. Okay.
Is that a promise?
What's that?
Is that a promise?
What's that? That the whole final?
Final's all-
Oh, no, absolutely not. Sorry. Sorry. Okay, guys, so another type of thing that I think is really important for you to know about graph theory is isomorphism. I noted this last time, that isomorphism, iso meaning same, morph meaning shape. So there could be 2 graphs that look different, but in graph theory are exactly the same, okay? That's not true with functional analysis. Like if 2 functions have different graphs, they have different equations. These don't necessarily follow equations, okay? In fact, functions are the heart of Cartesian graphs. At the heart of graph theory graphs are matrices. Okay, so for those of you guys that ever want to do anything more with graph theory, you'd have to know a little bit more about matrix theory. Okay, which isn't too difficult, unless you take it online, then it's not so nice. All right. So I want to show you guys how to determine if 2 graphs are isomorphic. Okay, and then I'll show you guys how they're not isomorphic. Essentially, what you want to do is you want to show a one-to-one correspondence between E of G and E of G prime. Okay, so let's call this graph G, and let's call this graph G prime. And somebody remind me, what does E of G mean?
Edges of
The edge set, right? So there's a one-to-one correspondence between the edge sets of those. There's also a one-to-one correspondence between V of G and V of G prime. Okay. So that's what we're looking for. Now this example is extremely easy, okay? Most of you guys can look at this, and what do you notice? If you turn this guy, like if you pull it up this way, it looks like it's going to be isomorphic, right guys? It'll look like it's the exact same graph, just a square, okay? Here's how we do this, guys. What we're going to do is we're going to make a one-to-one correspondence between the edge sets, okay? So I'm going to call this E of G, and what I'm going to do is I'm going to do a mapping to E of G prime. And I think the easiest way to do this is just to draw some Venn diagrams with this. Okay? Now, not like Venn diagrams where we did at the beginning of the course, but you guys know what a function is. Function basically has a domain, and this has a domain as well. So we just want to see a one-to-one correspondence between the domains. Okay? So let's say for some reason I started with U1. So I have U1. What vertex might U1 map to in G prime? Yeah, we could map it to V1. Is that the only one we could map it to? Yeah, we could. In fact, if you really wanted to, couldn't you map it to any of the 4 vertices?
Yeah.
You just have to flip it around a little bit. Donnie, that's what I would have done too. I would have mapped it to V1. Okay? So all you guys are going to do is just say V1 and U1 are mapped together. By the way, you guys know what one-to-one means. One-to-one means it passes the horizontal line test. Okay? Just in case you didn't know that, but one-to-one means that there's only one output, or there's only one correspondence for each of these. Okay? Now we have to be careful. Let's say I pick U2 next. Okay? There's only 2, now that I've defined U1 and V1, there's only 2 possible vertices that this could map to. So does anybody think they might know one of the 2 vertices that U2 might map to? V4, right guys? What's another one that it could? V3, right guys? It doesn't matter, but here's what I also do. It's like sometimes I'll do different shapes and I'll just draw like bisectors just to remind myself what I've already done. Okay, so we're going to say that U2 is going to map to V4. Okay, now these are the edge sets. Let's say for some reason I picked on U4 this time. So use a square there. Okay. I think there might only be one way to do this. Okay. What's the only vertex that U sub 4 must map to?
U3,
V2, right?
V2, yeah.
Because can't you go from U2 to U4 in one traversal? If you want to go from V4 to V3, what's the minimum number of traversals? 2, right?
Yeah.
The only way that you guys can go from V4 to another vertex in one traversal is to go to V2. Okay, does that make sense, guys? When I say one traversal, I mean you draw one line. It's one vertex, and then the edges incident upon that vertex. Okay? All right. So U4 would map to V2, I think you said, right? And now here's the tough one, okay? What must U3 map to? Wow, you guys are awesome. Check that out, okay? So I'm going to put a star over there. Or at least it wants to be a star. Yeah, it's pretty demonic anyway. So.
Sacrifice
Yeah, I feel like I should be sacrificed right now.
Or nothing, because spiral would be nothing.
Guys, does that make sense as to what I'm saying when I talk about a mapping? You basically just make sure that each of the vertices, you can traverse it, okay? So, for instance, we said that U2 map to V4, okay? And we put 2 lines there. And then V2 mapped, so to go from the square to the star, that is 3. And then over here. So, and I don't know if that helps out, but at least it shows the congruence, if you would. Now, when I say congruence, okay, don't get mistaken when I say congruence in the geometric shape that, or geometric term that you're used to. What does congruence mean, like in the geometry that you guys are used to? Congruence means that what?
Ratio to size.
Yeah, and this one, it doesn't have to have any ratio, right? Like for instance, remember I showed you guys like the squiggly, and that means the exact same thing. So congruence in graph theory actually means it's mapped. Okay, so I don't want you guys, when I say the word congruence, to confuse that. Okay, I'm going to do the exact same thing with the vertex sets. So I'm going to have the vertex set of G, and then I'm going to map that to the vertex set of G prime. G prime should be. Well, guys, what's the good news? Yeah. Yeah, it's already done, right? Okay. In fact, I'm sorry, this actually is the vertex, isn't it?
Yeah.
So this is actually V of G. Sorry about that, guys. Not that it matters that much. So that's actually V of G and V of G prime, because we mapped up the vertices. I'm sorry about that. Okay. And then we want to go ahead and map up the edges. What's that?
Yeah.
Yeah, you could do that, or you could just use the lines that we constructed. Okay? Yeah, you can define it as however you guys want. Okay? So doesn't it look like that line 1 has to map to line 1, right? We've already defined it. So diagonal 1 maps to diagonal 1. Okay, nice and easy. Diagonal 2 maps to diagonal 2, or parallel. Cat claws maps to cat claws. And then drunk guy trying to get at the bar at 2:30 in the morning maps to drunk guy trying to get in the bar at 2:30 in the morning. So he's clawing on the door. He needs one more Budweiser. Alright, does that make sense, guys? I mean, it's not meant to be difficult. Okay? Now this is a really easy mapping for this. Okay? What you're going to find is that not all isomorphisms are as easy. Okay? In fact, the next one's much more difficult than that. But let's just go ahead and try it. Okay? So I'll give you guys a minute to copy that down. All right. Now, by the way, I'm not going to give you guys ones that are not isomorphic. But and you don't have to write this down, but if you want to prove that 2 graphs are not isomorphic, It's actually pretty easy. Okay. To prove that two graphs are isomorphic, wouldn't one of them have a unique degree? Because if one has a unique degree, that means it's not the same shape. Okay. So one way to do that is that one vertex has a unique degree. Okay. Another way to verify that two graphs are not isomorphic is if the degrees of the graphs are different. Okay? Because that would mean that it's somewhere in there that there's an extra vertex. Okay? So they have to have, if they have a different number of vertices, the two graphs have different degrees. Well, I'm sorry.
Was the first one said?
Oh, one vertex has a unique degree.
Thank you.
Okay, sure, no problem, Don. We're not going to talk about bridges, but if one graph has a bridge and the other one doesn't, that's a way to verify that they're not isomorphic. Okay. If one graph is connected and the other graph is not connected, that would be a way. There's literally about a dozen ways to be able to prove that two graphs are not isomorphic. It's very, very easy to prove that they are not isomorphic. It's much more difficult to prove that they are, okay, which is why I'm making you guys do that. Okay, sure, no problem. All right, so let me go through and show you guys another example of this. Okay, a little bit tougher. Okay. All right, so we have these two graphs. They are indeed isomorphic. Okay. What I always try to tell people to do is start with the vertex set, okay, and then try to identify vertices with any unique degree. Okay, if it has a unique degree, then that's an easy place to start. Okay, so let's say we have vertex set of G, and we're going to map that to the vertex set of G prime. Okay. Now, unfortunately, if we look at this graph, guys, are there any vertices between graph G and G prime that have a unique degree? No. Okay, in fact, what are the only two degrees in the graphs for each of the vertices? 2 and 3, right? There's one right here with 3, and there's a whole bunch of them with 2, and there's a couple with 3. So wouldn't it make sense, guys, to start at the two vertices that have degree 3? Wouldn't that make it really easy for us? Then we pick off the other stuff, okay? Maybe you guys might remember somewhere like somebody told you, go for the easy questions first. Same thing with graph theory. Go for the obvious stuff first. Okay, so here's our sets. All right, I'm going to start with U4, or U sub 4. And what I want to do is I want to map that to something.
V5.
Now, there's only two places we could map it to, right? We could either map it to what two vertices in G prime?
V5 and what else?
V5 or V3. Right? Anybody think that it matters? It's a tough one, right? This one's not as easy. What's that?
It's only because they both have three coming from both.
Right. Guys, if you look about it, okay, there's really, if you think about what's going on, there's one traversal, okay, or I guess one walk, if you would, to where you have to go 2 to be able to get to the next degree of or 2 vertices to be able to get to the next vertex of degree 3, and then there's a couple of 2, okay? So I think you guys are absolutely right, because no matter what, you're still going to need to move 2 vertices to be able to get to the other one, okay? So let's do this. Let's map U4 to V5. In this case, it doesn't matter, but be careful. There might be some where it does matter. Okay. And then obviously, guys, what's the next very easy mapping? Yeah, 2 to 3, right? U2 to V3. Okay. And the reason that is because they're the only degree 3 vertices left. Okay. So whatever shape you want to use, dodecahedron, pentagram, whatever. U2, and then V sub 2. Now here's where it gets tricky, right guys? Alright. So
It's V3, not V2.
oh yeah. Oh, because I just wrote 2. Thank you. I'm sorry. I wasn't trying to do that on purpose. Just doing. Yeah. So at this point, I think there's a couple possible mappings that we could do correctly, okay? Does anybody think they might know another mapping that we can utilize? So, Jake?
U3 and V4.
So U3, okay, let me do a square on that one. And then V4, sir? Yes. Let's make sure that makes sense, okay? That means that I can move from circle to square to triangle in true traversals, right? I can move from circle to square to triangle in 2 traversals, okay? That looks pretty good to me, okay? I don't have any problem with that. Right? By the way, I think we forgot to use our lines, didn't we? So, we started with, I guess it really doesn't matter, but between triangle and square, there's 1 line, and then between square and triangle, there's 2 lines. Now, this is where it starts to get imperative that we do the right stuff. Oh, by the way, I have to do the mapping. don't I?
You have to,
So, hold on one sec. What do we do, squares?
U3, V4.
Thank you, U3, V4, I was getting there. Okay. Now we have to be really careful, because now it does matter, okay?
U1 to V6.
Yeah, I think
Yep.
U1, I'm gonna use the star again, as best as I can, that one might be better, to V6, right Lucas?
Yeah.
Nice, okay. Guys, that's the only possible way that that could work. Does that make sense as to why that is? Because if you want to move from circle to star in 1 traversal, you have to make sure you move from circle to star in 1 traversal. You have to make sure you move from triangle to star in 1 traversal, okay? Which I think we can definitely say that we've done. Okay? So I'm going to put 3 lines between circle and star. And then I'm going to put 4 lines between star and triangle.
Why don't we worry about the square?
What's that?
Why don't we worry about the square, how many traversals it takes to get to...
Oh, we do, yeah, it should actually. So to go from U1 to V6, it should take 2
Oh, you just
traversals.
didn't mention it.
Right,
Okay.
okay, it should take 2 traversals, okay?
Okay.
Which it does. No matter where you are on the star, it's gonna take at minimum 2 traversals. That's a good point. Okay, so sorry about that, I didn't mean to neglect that. Okay. All right.
U5
I
to
forgot
V1.
the 4 between, here, right?
Yep. So you do U5 to V1 and
Yeah.
then
So circle.
U6 to V2.
So U5, I'm running out of stuff, so I'm going to double circle. There we go. So U5 to V1, because we have to go 1 circle to 1 circle, or 1 circle to 2 circle, in 1 traversal. Okay. And then U6,
V2.
yeah, to V2. So I'll map these in a second, I'll draw them out. I'm just trying to think of a shape that I could use. Flat,
Got like a really complex, like Mona Lisa.
You're an octagon.
Yeah.
there we go. That works. Hexagon. Okay. Does that make sense to everybody, guys? Not too difficult, right? A little bit sneaky, but you just have to make sure there's that 1-to-1 conformity between them. So we said that U4 maps up to V5. Oh, we already had that one, sorry. We were on star, so U1 maps to V6. And then we would have U5 to, what was it down to V1? Thank you, sir. U5 to V1. And then finally, go ahead, sir. U6 to V6. I just ran out of room, so we'll just loop it in. Inclusion. Let's try to make sure that didn't look dirty or phallic in any nature.
it's kind of hard to read. What you,
What's that?
U6 to V2, yeah.
Oh, we said.
We already did V6.
Okay, sorry. Yeah, V2. Okay, sorry. There we go.
so you said what, U3 to, what is the thing you wrote? I couldn't read them.
Let me erase it. I'll do it again. So this is U1. This was, I think we said U5
U5 to V1
to V1
and U6 to V2.
and U6 to V2, right?
Yeah.
What's the third V?
I'll erase it, I'll start it again.
Just write
it on the big board.
Yeah, that's fair. I mean, you guys could just look at this and figure it out, right? I mean,
Alright.
that's all right.
What about the,
I'll cater. I'll bail down to the needs. So, fine. So we have V of G and V of G prime. All right. So. We had circle matches the circle, so U4 matches to V5.
So 4 should be IIIV, or I,
What's that?
no, VI,
yeah.
or IV.
Okay.
It should be like.
All right then, U3 matches to V4. And then what else do we have? We have U2 matches to V3. And then we have, what else do we have? What did we start already? U1 maps to V6. And then we would have the U5, which maps to V1, yep, thank you. And then we have, yeah, U6 and then V2, thank you. Okay, so, there we go. So, any other questions, guys, I can answer about this? Okay. What's up?
The 3 edges we haven't marked yet.
Right, I'll go ahead and do that. So, I marked this one with a V, so just like as in 5. And then, for the other ones, I'll mark this as VI, which means that, for our circle to double circle would be V, and this would be VI. And then V2 to V3.
Check marks in the triangle.
So we can make that VII. And then you guys can copy that down, so hopefully. So, any questions, guys, I can answer about how you guys are going to do the mapping for this? Okay, all you basically do is, like I said, just map things up from vertex to vertex, from edge to edge. I'll keep the edges open for you to make it easier for you, okay, just because I think that might be the easiest way to do it. Okay. So the last topic we're going to take a look at this afternoon is we're going to take a look at trees. Okay. Tree means that it's a connected graph with no circuits. Okay. So basically, if you can start on a vertex and you can go through and end up on the same vertex without doing a closed walk, then, or I'm sorry, a circuit on there, that means it's not a leading edge. Okay. A tree with n vertices has n-1 edges. We won't prove that, but we can prove that by mathematical induction if we choose to. All right, so let's go ahead and construct the following graphs if possible. Okay, so for letter A, I want to construct a tree. Okay, and again, a tree is a connected graph with no circuits. Okay, with 5 edges and 4 vertices. Okay, so anybody think they might be able to construct that?
Yeah.
Okay, that's a good answer.
So, start with the vertice at the top and draw 2 lines from that, right?
I think that works,
That's
doesn't it?
what I was saying,
Yeah, that's 5 vertices and 4 edges, right? Doesn't contain a circuit. Yeah. That's a tree.
Trying to make it look like a tree.
I mean, you can make it look like whatever you want, I don't care. Does that make sense, guys? Not meant to be difficult, okay? That's probably the easiest way to draw a tree is just do your straight line and then put your vertices in the middle of it. Okay. For part B, tree with 7 vertices and 7 edges. Okay, so how do you guys do that?
Not possible.
Not possible. How come, John?
Because a tree with n vertices has
Yep. N vertices and n-1 edges. Okay, just in case I didn't say it, make sure you always go back to the definitions at the top. Ensure that what we have as the definitions works for whatever you're trying to do. Okay, so that's why I do it for you guys. So, not possible. Okay. If it has 7 vertices, should have 6 edges, so 7 vertices implies 6 edges. At least for a tree, right? For other graphs, then that's not necessarily the case. Although it could be, but it doesn't necessarily have to be the case. Okay. Guys, any questions about those? Okay, really easy. For letter C, maybe not so easy. Okay, this one does work, by the way. Okay, we have a tree with 11 vertices, 10 edges, total degree of 20. 3 vertices must have degree of 3. Okay, so certainly this one's a lot more difficult, but it is certainly possible. Okay, so I'll start you out. How nice of me. I know. You're welcome, Tom. Not a problem. Anything for you, buddy.
That was the hardest part.
It was. Sometimes the hardest part is just getting started, right? All right. So any suggestions as to perhaps how we can do this? So,
I was gonna say, could you make like a line with stems that come down to get those extra vertices?
so like, and then branch off of this one, Jacob, or?
Well, I could just going across and then going down. I don't know if that would work.
Well, remember, you have to have some of them that have a degree of 3. So,
Yeah, so I had,
Three of them with
so I
three
had
lines.
like on A,
Okay.
that middle point,
oh, this guy right here?
yeah.
Okay.
So I just did like what you had on A in a straight line.
Okay.
I just had one that branched down.
Oh, I
so
see.
that got
Okay.
bigger.
So like this,
Yeah,
and then this guy right here, like that?
yeah,
Okay. And then you just kept having like more of that stuff?
yeah.
Okay. So we just had, and then another one that branched down, sir? Okay. And then another one that branched down?
Yep.
Okay, because that would give you your 3
Yeah,
vertices of degree 3, and then you finished it off like this, sir?
Yeah, just make sure that I had enough edges and vertices.
Yeah, because it doesn't necessarily say like how many degrees, 1s and 2s that it has to have. Okay,
Couldn't
so,
you have also just started with 3 vertices having a degree of 3, so just draw 3
Yeah.
different sections and then connect those?
sure, there's a number of ways to do this, okay? Unfortunately with this stuff, guys, there's no algorithm, if you would. You kind of have to do the trial and error that Mr. Purvis did with that, so that's. If I look at this, I have degree 1, 2, 3, 3, 3, so at least that makes sense. Degree 1, 1, 1, 1.
There are total 9 vertices so far,
Except
right?
that's only
Yeah.
Okay, so we'll just draw one more, right?
You gotta go, yeah.
Okay, so we'll draw one more. So this guy now has a
Well-
degree. Does that work?
Except that's 10 vertices, you need one more vertex.
Okay. So
Yeah,
we'll
you
just
need one
draw-
more edge
Okay,
and another vertice.
There you go.
okay. Oh, I see what you're saying, Jacob. Sorry, I just didn't go out enough. Okay, so this will be a 2 and 2. Okay. Let's see if this works out. Hopefully it does. So 2, 5, 8, 11, 13, 13, 3 is going to be 16, 17, 18, 19, 20. So, I don't know, it looks like a dog with a really long neck, I guess, and 3 legs. Or actually it has 4 legs, just no tail. Poor guy. So it's like a giraffe dog. I don't know, what dogs have long necks? Snoop Dogg? Oh, it's Snoop Lion, isn't it? My bad. I forgot. So, he changes it every week.
Does he really have a long neck?
I don't know. Questions I can answer, guys? Okay. Construct all non-isomorphic trees with 4 vertices, okay? Now, remember we talked about what it means to be non-isomorphic, okay? One vertex has a unique degree, different number of vertices, 2 graphs have different degrees. So we should always ensure that we go back to this when we talk about non-isomorphic, and these are basic cases, okay? So we need to have 4 vertices, okay? What's probably the most basic tree with 4 vertices?
Square.
That's not, no, that's a
that's
circuit.
not a line.
Can't- A line, okay, probably a line, right? Can't have a square, right, because that contains a circuit, okay, almost a square. Okay, so this is 1.
It's not touching.
There you go. The broken square.
Okay.
Almost this.
What's another non-isomorphic graph?
And you,
Okay, well,
could you do that?
That's
It's
the
not
same
complete.
thing.
It is,
Donnie, go ahead, what were you saying, like this, like 1, 2, 3?
yeah.
Donnie, unfortunately, that's isomorphic, because couldn't you just spread that out, just like this, like pull it down? And that would be isomorphic. So, okay, that's okay, that's not a big guess. You're wrong, but it's not a big guess. It's okay. You guys are gonna go with you, at least in front of everybody else. Alright, another suggestion, guys? Alright, how about this? What if I did,
Yeah. That's what I was just.
that's what you were just, got it. Why is that non-isomorphic to the first graph?
Because they're looking at different degree.
One has unique.
Correct, okay? There is a unique degree of 3 in that second graph, isn't there, guys? The first graph has two vertices of degree 2. That has a vertex of degree 3 and 3 of 1, okay? So remember, as long as you have different degrees, then you have non-isomorphic graphs. Okay? Anything else that you guys might think of that might be non-isomorphic to either of those two? It's actually good. Oh, go ahead, you.
Like a plus sign,
Okay.
and then it would have to be a grade 4, if you have a vertice in the middle.
So, like that,
Five vertices.
and then we can only have 4 vertices, so it would have to look like that.
But
But that's actually the
the
distance. Because if you just flipped it over,
Yeah.
so, that's okay, it's not a big guess, but that's not it. There's actually no more, okay? Because remember, a tree has to be connected, okay? So at minimum, okay, you can have degree 2, okay? And then you can just work from that. The way that I usually work it is I start with degree 2 and then go to degree 3, then 4, then 5, etc., depending on how many vertices I have to work with, okay? Basically exhaustion, if you would, okay? Does that make sense, guys, with these? You just go ahead, start with vertices of degree 2, and then try to draw one that has degree 3, and then draw one that has degree 4, and then one that has degree 5, etc. Okay, just depending upon how many vertices. Okay. What is the total degree of a tree with n vertices and why? Okay. So this might be a tricky question. Okay. But there might be an easy way to be able to try to figure this out. Okay. Now I'm not asking you guys to prove it. I'm just asking you guys how many there are. Okay. Wouldn't it be good for us just to draw something like each of those and figure out the degree? Okay, so if the total degree of a graph is 0, okay, or a tree is 0, okay, guys, what does a tree with degree 0 look like?
Just a point.
Just a dot, right?
The-
Just a dot. Okay, so that has degree 0. Okay. Let's say we have one vertex. Okay. Well, actually, no, it's like that. So degree would be 0. Okay. Degree 1, so this has, let's do this. Let's have a column here. So we have vertices, okay, and we're going to have our degree. Okay. So if it has degree 0, I'm sorry, if there's 0 vertices, then the degree of that graph is 0. What's the degree of a tree that has 1 vertex? 0, right? Remember what degree is. How many sticks are sticking out of it, right? So it's okay. That has no degree. Okay. Let's say we have a vertex of degree 2, or 2 vertices. Okay. Well, I just told you. That would be 2, wouldn't it, guys? Okay. Does that make sense to everybody, guys? I'm just figuring out, this has 1, this has 1. Okay. Let's say we have 3. Okay. How many what's the degree of that graph?
2.
Nope.
No.
4.
4.
1, 2, 1. So that's 4, right?
Oh,
Does
yeah.
that make sense to everybody, guys? Okay. If I have 4 vertices, what's the degree of that graph? 6. Okay, so that would be 1, 2, 2, 1, which is 6. If we have a graph of degree 5, it's almost like we're using what, guys? The method of iteration. It's almost like we just learned that for some reason. Like I'm trying to connect ideas to you. What? Yeah. Yeah. So this has a degree of what, guys? 8? We'll just do one more because I think most of you might be able to figure out what's going on with this. Okay. If I have 6 vertices, 6, we have 1, 2, 2, 2, 2, 1, having degree 10. So, if I wanted to figure out, now notice I'm not adding these up, okay? It's not like what you guys just handed in for homework, okay? I'm not adding these up, I'm just trying to figure out the total degree of a graph with n vertices. Okay? Does anybody think they might know what that is? Just looking at what we have there and matching it up to the number of vertices? 2n minus 2, or if you factor in 2n minus, or 2 quantity n minus 1. Nice. So we could have 2 quantity n minus 1, which is the same as, John, you said 2n minus 2, correct, sir? Very nice. See if that works, guys. Throw in something that like 3. 2 times 3 minus 2 is 4, okay? 2 times 6 minus 2 is 10. It looks like that works. And guys, doesn't it make sense every time that you add an edge, aren't you increasing the graph's degree by 2? Okay? That you could prove that very easily by mathematical induction, okay? For this graph, we're just going to say that that's what it is, okay? But we're not going through and trying to actually prove that on this. By the way, this is only true, right, if n is greater than or equal to 2, right? Or actually greater than or equal to 1. Yeah, it'll work. Okay? It doesn't hold for 0, okay? Because then you get a negative 2, which just doesn't happen. Okay. So we always want to make sure that we put a domain on this. Okay. Any questions about the graph theory stuff, guys? Okay, hopefully not too difficult. Hopefully it's probably some of the easiest stuff in the course. Okay, so this is it that we have to learn. Okay, so remember on Monday, guys, that if you have some questions about the final exam, we're going to answer those questions. Make sure you bring me some questions that you might have. A good way to study for the final is look at the old examinations. Okay, I have the solutions posted online, so you guys can do that.
Are you gonna do a practice exam or not?
There's one posted online.
Okay, I
Yeah.
have it online.
So yeah, look online, download the practice exam, see if there's problems on there that you guys just can't answer. Okay, if there's problems on there, those are the ones that you want to ask me about. Okay, if you can answer everything, then good for you. Okay. Oh yeah, we'll talk about the reference sheet. It's going to be more than just the note card because obviously it spans 3 examinations plus new material. So, if you want to bring your old note cards, that would be fine with me, and then just make one more note card. That I don't have a problem with that.
So
Okay.
you can make 4 note cards, I guess.
Yeah, I guess that would be fair. Okay. I don't have a problem with that because I mean that's what you guys needed for each exam. That should be good. Okay. Other questions I can answer for anybody about anything? Okay. All right. So I'll be here for a few minutes if you guys need assistance with anything. If you didn't give me your assignment, now is the time. Actually, 3:15 was the time. So make